Okay, this is the lecture video for MAC 1114 trigonometry. We're in section 9.5 where we're going to continue to look at properties of vectors, specifically the dot product and the applications of the dot product. So in the first formula box, you see the dot product of two vectors, and as we studied in the last section, a vector has a horizontal and a vertical component called A and B, and then we could have another vector that also has a horizontal and a vertical component, so that if you want to multiply these two vectors, which is referred to as the dot product, one vector multiplied by another, it is nothing more than front component times front component. In other words, multiplying those horizontal components, that's what A times C is, then added to back component times back component. So B times D, that's that back component, and then you'll be adding those together to get a scalar. In other words, you're going to have a numerical value for your final answer there. So a dot product is a scalar. It's just a value. Okay, then we have properties of the dot product. When you're doing a dot product for two vectors, finding the product of two vectors, it doesn't matter whether you have the vector u first and then v, or whether you have v first and then u. So this dot product is commutative. Okay, when you're multiplying a vector by the sum of two vectors, that would be the same as distributing in that dot product, so that it would be the dot product of u times v plus the dot product of u times w. Each time you do a dot product using the formula that you got here. And I'll be demonstrating that. And these are just all those properties. Same thing that's going on right here. Here you're distributing vector w into this sum. So it would be w times u, doing the dot product there, plus w times v, doing the dot product there. This shows a scalar times a vector, then multiplied by another vector. So if you were asked to do something like this, you could drag the scalar into vector u first, and then do the dot product with v, or you could do the dot product and then multiply by the scalar. Okay, then we have 0 times vector u. You're doing the dot product of 0 times a vector, and that is just 0. And then if you have the dot product of vector u times vector u, that's the same thing as u squared, the vector u squared. So just different things that you can do with the dot product. The geometric interpretation of the dot product, I've included that here for you as well. And so geometrically, it can be explained in this way. If theta is the angle between two vectors, non-zero vectors u and v, where theta is between 0 and 180 degrees, then this is the way that you can find the angle using the dot product, thus relating the dot product to the angle that is between them. So the dot product is the magnitude of the dot product of u and v is the magnitude of u times the magnitude of v, length of u times length of v times the cosine of the angle between them. This theta represents the angle between the vectors. So if we were to isolate cosine of theta, we would be taking dot product of u times v and dividing it by this product, magnitude times magnitude. And thus you have the formula for finding the angle between two vectors. Angle between two vectors is given in this way. Cosine of that angle between the vectors is just dot product on the top divided by product of the magnitudes. And I'll demonstrate that as well. So these are the formulas that you're going to be using right away as you tackle these problems. We also like to be able to determine whether two vectors are perpendicular. This is just another name for perpendicular. It is the word we use when we're talking about vectors. Rather than perpendicular, we call them orthogonal. So here's how you tell whether two vectors are perpendicular, or in other words, orthogonal. If the dot product is equal to 0, then the vectors are perpendicular. They are orthogonal. Okay, so let's highlight that. If the dot product is 0, your vectors are orthogonal. And the way that you can tell whether they're parallel is that one vector is a multiple of the other. That tells you that the vectors are parallel. I'll be demonstrating that as I go through the first 3 examples, because you're going to be asked this quite often to determine whether the vectors are perpendicular or are they orthogonal. That's a tongue twister. Okay, so just going over some of the properties with you and how to tell whether they're perpendicular or parallel. Okay, so you see that in numbers 1 through 4, you're doing all 3 things that were introduced on the previous page. We're going to find the dot product. We're going to use that dot product to find the angle between the 2 vectors, and then we're going to state whether the vectors are parallel, orthogonal, or neither. And based on this determination of whether they're parallel or perpendicular, orthogonal is the same thing, does that make sense with respect to the answer that we got for part B? So one answer backs up the other. Okay, so in part A, let's first do the dot product. Okay, we're just going to do V times W. I'm going to go ahead and write out vector V in component form. 5, 4, and we are doing the dot product of that vector with vector W, which is 4, negative 5. Okay, that formula was front times front, so 5 times 4 plus back times back, 4 times negative 5. Okay, this is 20 for the front product plus negative 20 for the back product. Okay, so then we're going to find the angle in between the vectors. Now you can already tell from the answer that we got here. Look and see how the dot product came out to be 0. When the dot product is 0, this was one of the properties we learned on the previous page. When the dot product is 0, you can expect that means that the 2 vectors are orthogonal. In other words, they're perpendicular. Well, if they're orthogonal, if the 2 vectors are perpendicular, that means they meet at a right angle. If we can recall what perpendicular means, that means they meet at a right angle, or in other words, there's 90 degrees between them. So you can already predict what you're going to be getting, what kind of answer you're going to be getting for part B. Okay, here's the formula for finding the angle between the vectors. Cosine of the angle between the vectors is the dot product, which we already found in part A, but I'll write the formula out, over the magnitude of one of the vectors times the magnitude of the other vector. Okay, here is that work. Dot product, we got 0. I mean, so I don't know if it really matters to go and do the magnitude, but just so you can remember what a magnitude is, I'm going to go ahead and write it out. Magnitude is the length of the vector, and that is just 5 squared plus 4 squared times, then you're doing the magnitude of the other vector. The other vector here was 4 squared plus negative 5 squared. And I'm only doing, I mean, I realize that if it's 0 at the top, you're going to get 0, but just to remind you how to do a magnitude so you can carry it out in the rest of the problems. So the magnitude here would be 25 plus 16. 25 plus 16 would give you 41. Square root of 41 right there for that one. That would be the magnitude, or in other words, how long vector v is. This would be the same thing, 16 plus 25. So again, you would get square root of 41. So square root of 41 for this one, square root of 41 for this one. That product, because you're supposed to be taking the magnitude of one times the magnitude of the other. And for a lot of these problems, you'll have to carry it out all the way, so might as well demonstrate what that work looks like. So you have 41 here, 0 here. Anyway, cosine of theta is 0 over 41, which is just 0. Let's bring that down here. Cosine of theta is equal to, we found out, 0. Well, what's theta then? We already know that these vectors are perpendicular. Otherwise, the dot product wouldn't have been 0. So we can write that when the dot product is equal to 0, that implies that the vectors are orthogonal. Let's practice that new word. I don't have enough room to write it all out, but I'll just put that. All right, so when we go to find this theta, it better be 90 degrees because that means there's a right angle between the vectors. How do you make your calculator find that? You could just go inverse of 0, and that'll be equal to theta. Just the value and the theta switch sides. So we still have our calculator in degrees from the previous section. So inverse cosine, pop in that 0. There you go, 90 degrees. And in fact, we have found out or verified that they are indeed perpendicular, because that's what orthogonal means. A dot product of 0 already indicated that, and we have further verified it by calculating an angle between the vectors of 90 degrees. So part C, it's already been said. State whether they're orthogonal, parallel, or neither. They are orthogonal. We knew that right from the answer in part A. Okay, moving on to example 2. All right, so now we have this, and you can leave them in this IJ form. You don't have to write them in component form, as I very often do, just because I like that form. It's nice and neat. You can leave it right in the IJ form, and I will just do the problem right from that state in example 2. Okay, so dot product. We're going to do V times W, and that just means front component times front component. The component, those components A and B are the coefficients, so it's square root of 3 times 1 plus back component times back component. Coefficients are -3 and -1. Those are coefficients of your J components. So that is square root of 3 plus +3. Okay, this definitely did not come out to be 0. We already know that they're not orthogonal. When the dot product comes out to be 0, they're orthogonal. Now, once you know that orthogonal is out of the question, you should check to see whether they're parallel. If they're parallel, then one vector is a multiple of the other. That's kind of, I don't know, easier to see when you write it in component form, but what could you multiply these coefficients by to turn them into these coefficients? I mean, there's nothing. This one, if you write it in component form, it looks like this. And if you write this one in component form, it's 1, -1. So oftentimes we try to ask ourselves, what do you multiply the smaller numbers by to turn it into these? Well, if you think it's 3, multiply this by 3 and this by 3, and you would have 3, -3. That's not what this one is. It'll get you the back number, but it won't get you the front number. If you think that what you need to multiply it by is square root of 3, well, multiply this by square root of 3, and yes, you will get that front number, but multiply that by square root of 3, and you'll have -square root of 3, and that's not what's back here. So there's nothing you could multiply these smaller numbers by to turn it into that. So it's not orthogonal, these vectors, and they're not parallel either. Otherwise, one vector would be a multiple of the other. We've already answered part C. Now as far as part B goes, find the angle between these vectors. That is a very specific formula. It is the dot product on the top, magnitudes, the length of each vector multiplied on the bottom. So that dot product, we already found it. It was square root of 3 plus 3 at the top. And then the magnitude of V would be, let's see, I can do a little bit of it right here. Be square root of, okay, we're going to take the front component and the back component and square it. So it's square root of 3 squared plus, let me make this a little bit longer, plus negative 3 squared. Okay, so when we square each of these, this would be 3. This would be negative 3 squared would be 9. So underneath this first radical signifying the magnitude of V, that's what I'm trying to carry out right now. I'm doing the work for it. I would get a 12 underneath the square root. So that represents the magnitude of V. Now I have to do the magnitude of W, and I have to multiply these together. So magnitude of W, okay, let's see, what do we have for W? We have a 1 and a negative 1. So its magnitude would be 1 squared plus negative 1 squared. It'd be 1 plus 1 underneath that radical. So that radical would have a 2 underneath it. So you have one magnitude that's represented as square root of 12, and the other magnitude represented as square root of 2. So you're having to go all the way with this. I did the dot product at the top. I did the magnitude of V. I found the length of it using its coefficients, each one squared underneath the radical. I got a 3 and a 9, giving me 3 plus 9, which was 12. Then for the magnitude of W, I used the components of the I and the J again, which were 1 and negative 1. That gave me 1 squared plus negative 1 squared, which was 2. Now when you have the same kind of radicals multiplied together, you can bring them up underneath the same radical just to have something more simplified to feed into the calculator. Square root of 12 times square root of 2 is square root of 24. Okay, so now what you want to do is bring this to a single decimal so that you can figure out what is the theta. So we have cosine of theta is equal to, we're going to feed this into the calculator. Square root of 3 plus 3 is the numerator divided by square root of 24. Okay, so at the top, square root of 3, close it, plus 3. With that calculation, divided by square root of 24, and that turns out to be 0.9659. I'm going to go 593. Some more decimal. I mean, you're going to have the whole thing in there anyway, so you're going to get an exact answer. But just have something to put right here. I got all of this, whittled it all the way down to 0.96593. Okay, and then don't lose track of that skill where you're finding an angle just by rewriting this as the inverse. Now, there's no such thing as reference angle here because you're just finding the angle in between two things, not spinning to a particular quadrant. So it's inverse of 0.96593, even though you're really going to be feeding in the whole thing, and that's equal to theta. Just switch the numerical value and the theta, the sides that they're on, and that allows you to introduce the inverse, which can now be put into the calculator. So inverse cosine, dump in that answer by pressing second answer, and you get that it is 15 degrees. Okay, so it makes sense that we had decided that the answer that we got for this dot product, it wasn't 0, so it couldn't be orthogonal. And when we checked out whether there's anything we could multiply these numbers by to get this, in other words, is this a multiple of this? Well, if it is, if these bigger numbers are a multiple of this, there should be something you could multiply both of these numbers by to get both of those numbers, and we decided we couldn't do that either. So they're not parallel and they're not perpendicular. And so we say that they are neither. They are neither parallel nor are they orthogonal. You can just say neither. And that kind of confirms that they're not orthogonal because there would have been 90 degrees between them. Okay, moving on to example 3. In example 3, once again, you have your two vectors, and you are using the same instructions for numbers 1 through 4. We're going to figure out what the dot product is. So V multiplied by vector V multiplied by vector W is, and again, you can leave them just in this IJ form. You can go at that dot product right from here, or you can write them in component form if you like to look at them like that, where you're just have the coefficients. That's what they look like when they're in component form. You can think about doing the dot product right from that point, 1824. To me, it just makes them easier to look at these. But anyway, it's front times front, so I'll write that out. Negative 3 times 18 plus back times back. That's negative 54 plus negative 4 times 24, so plus negative 96. This is negative 150. Okay, so that's my dot product. Now, I already know right from this answer right here that these two vectors are not orthogonal. Otherwise, the dot product would have come out to be 0. In part B, so when I go to find the angle, it's not going to be 90 degrees because I would have gotten a 0 here for the dot product. So let's go ahead and find the angle between the vectors anyway, which is the dot product answer divided by the magnitude of this vector times the magnitude of the other vector. So the dot product was negative 150. And then now we're going to go and do the magnitude of each. I'll do a little bit of work right here. So magnitude of V, let's see, we have negative 3 squared. And then the other component was negative 4 squared. So this is 9, this is 16. Add these together, you have 25 underneath that first square root, which is 5. So that is the magnitude of vector V when I work it all the way down to 5. Now I'm going to find the magnitude of vector W, which has an 18 and a 24 as its coefficients, which is all you use when you're finding the magnitude. You're going 18 squared plus 24 squared. Okay, those are some big numbers. 18 squared plus, let's see, what's the other one? 24 squared is 900. So this is, we end up with 900 here after we do 18 squared plus 24 squared. And the square root of 900 is just 30. This ends up being negative 150 over 150, which is negative 1. So simplifying this all the way down, this big formula where we needed the dot product answer on the top, grabbed it from part A. We needed a magnitude of V. We needed a magnitude of W. This came out 5. This came out 30. We multiplied them and got 150. This divided by this is negative 1. So now we're at the point where we know cosine of some angle is equal to negative 1. And you may just be able to do this in your head. You may not need your calculator. When you rotate to negative, when you rotate to what angle is the cosine negative 1? Now, that may be hard for you to think of in your head, but, if you do remember the unit circle well, remember that when you rotate right over here to 180 degrees, which can also be called 1 pi, you can give the answer either way unless they specify that they want it in radians. You can give it in degrees. But anyway, if you're on a unit circle where the radius is 1, you're out at negative 1, and the y-coordinate would be 0. This represents the cosine. So where, at what angle is the cosine negative 1? At an angle called 180 degrees, which is the same thing as pi. If you want to put that in your calculator, then put it in your calculator as an inverse. It would be inverse of this value is equal to the theta that we seek. So second inverse, put that negative 1 in there, bam, 180. Okay, so this is the angle between the vectors. If you were to plot this as a point, negative 3, negative 4, and draw a vector out to it, and then plot this as a point and draw a vector to it, there would be 180 degrees between those two vectors. Okay, then in part C, where we're describing, hey, are these orthogonal? Are they parallel? Are they neither? Okay, we already know that they're not orthogonal. Why? The reason that they're not orthogonal is because the dot product was not equal to 0. Okay, are they parallel? All right, well, let's see. Is there something that we can multiply these smaller numbers by to get these? Is there a single scalar multiplier that we can multiply both of these by to get this? Well, it looks like there may be. If we multiply, let's say, negative 6, because I can see that's what's required for that, but will it work to get that? If we multiply this vector, the components of this vector, this times this would give us 18, this times this would, yep. So this is considered a multiple of the first vector. And what you need to multiply it by is actually negative 6. So we're going to say, yes, these are parallel since, and this is the reason, since negative 6 times one of the vectors is equal to the other vector, the two components of the other vector. Therefore, this is said to be a multiple of the vector V. So yes, they are parallel. Okay, example 4. In example 4, we have vector V, which is negative 5 on that I component, 0 on the J component. For vector W, For vector W, we have 1 on the I component, 0 on the J component. So when we do part A, where we do the dot product of these two vectors, it is negative 5, 0. I'll keep this one in component form, times 1, 0. And that's just the formula, which says it's front times front plus back times back, which is just negative 5. Okay, your dot product is just a scalar. It's a value. All right, we know that they're not orthogonal. These vectors are not perpendicular. Otherwise, that dot product would come out to be 0. Are they parallel? Is there anything that you could multiply these two numbers by, some number that you can multiply both of these components by to turn them into those numbers over there? And that scalar would be negative 5. If you were to multiply both components of this vector by negative 5, well, this times this would be that front component, this times this would be that back component. So V and W are actually parallel. This is a multiple of this vector right here. So in B, let's find out what the angle between them is. It's cosine of theta is equal to the dot product that we just found in part A, which was negative 5. And then we're going to do the magnitudes on the bottom. So the magnitude of V multiplied by the magnitude of W. Okay, magnitude of V, let's see, those components are negative 5 and 0, so it's negative 5 squared plus 0 squared, and that's just 25. Square root of 25, 5. So it's 5 times, and then magnitude of W. Okay, well, the components of W are 1, 0. So it's 1 squared plus 0 squared. So that's just 1. Square root of 1 is 1. Okay, so this is negative 5 over 5, which is equal to negative 1. What is the angle associated with negative 1? We just talked about this in example 3. When the cosine of theta is negative 1, that means your theta is 180 degrees, or pi. You could call it pi, which I showed graphically, and we also did in the calculator. Both times we got 180 degrees. So theta would be 180, again verifying that they are not orthogonal. In other words, perpendicular. That is the angle between them. And part C, no, they were not orthogonal, but we did determine that they were parallel, and that is more or less you're just eyeballing both of the the components of both of the vectors and seeing, hey, can you take the smaller ones and multiply by some scalar that would show you that the other vector is a multiple of these smaller numbers. And we said that that scalar that could be used to multiply by both of these components would produce the other vector. So yes, you can write it even like this. Vector V is parallel to vector W, since this vector 1, 0 can be multiplied by negative 5 to produce the other vector. That means negative 5, 0 is a multiple of 1, 0. Okay, so they are parallel. Okay, moving on to example 5. So tons of practice doing the dot product, then using the dot product to find the angle between the vectors, and determining, using the dot product, and also the answer in part B, whether or not they are parallel or or orthogonal. Okay, so now we come to vectors, the IAJ form. And okay, now so let's see. Oh, so A represents a coefficient in this one. Find A so that the vectors I minus AJ, so A is just a coefficient of the J term this time. And then here's another vector, 2I minus 5J. We want to force these to be orthogonal. Well, if they're orthogonal, that means that the dot product is 0. So we're going to force the dot product to be 0 so that we can find the A value. Dot product has to be equal to 0 for this to be true. Okay, let's do that dot product. Remember, you're just multiplying, and we can write this in component form if you want. Component of the I term, 1. Component of the J term, negative A. So this is like the coefficient of the I term, coefficient of the J term. That's for V. And then for W, if you want to put it in component form, it's just 2, negative 5. So that when you're doing the dot product, you're multiplying front times front, so 1 times 2. And I'll show my work, even though I'm sure you can do it in your head. The dot product goes on to add the back component times the back component. Negative A times negative 5. And we want this dot product to be equal to 0. Okay, let's bring this and this down. So this is 2 plus negative A times negative 5 is 5A. We have ourselves a nice little equation, and we solve for A. All we were being asked to do is find A. So minus 2, we end up with 5A equal to negative 2. And then to finish this, we would just be dividing the 5 right off of the A. So divide by 5, and we have A is equal to negative 2/5. That's the value or the coefficient that would have made this vector orthogonal to vector W. Okay, then we come to decomposing vectors, and this is something that's used pretty heavily in physics classes when you're trying to take a vector and decompose it into its horizontal vector and its vertical, and not its horizontal vector, but its parallel and its orthogonal vector. Okay, so decomposition of vectors. We have the formula right here. It tells you that to decompose a vector into two vectors where V1 is parallel to vector W and V2 is orthogonal to vector W. So there's some vector that they want you to take and decompose this vector V into two vectors, one that is parallel to this and one that is perpendicular or orthogonal to that vector. Okay, this is V1 will be the one that's parallel to the other vector. Okay, this is how you get the one that's parallel to W. And this will be the one that's orthogonal to W. Okay, two different formulas. So this vector V2 will be this vector V1 will be parallel to W, and this vector V2 will be perpendicular to W. Okay, here we go. Okay, so to do V1, you're doing V times W, the dot product that we've been using the whole section long. So dot product of V and W is going to be front component times front component, 7 times negative 1. It's just those coefficients, plus 3 times 1. So we got that dot product on the top, and we're multiplying that by vector W, that whole vector W, which is, I'm going to put it in component form, -1, +1. We don't want to forget that. Okay, all of this on the top, and then we're going to do the magnitude of W down on the bottom. Well, here's W. This is vector W right here. So if you do the magnitude, it's just each of these components squared. Magnitude is you're doing the length of that vector. Okay, let's clean this up a bit. Right now, all we've done is throw everything into the formula. We did a dot product of V times W at the top, multiplied by the actual vector W off to the side. When anything's off to the side like that, it really belongs to the top. Okay, so, and we can put this in IJ form at the end. I'm just going to keep it like this for right now. So we got -7. And we're going to take everything that we get here and multiply it by that vector W. Okay, so it's -7 plus 3, which turns out to be -4. And that -4 is going to be multiplied by the vector -1, 1, which turns out to be, this is everything happening at the top. Okay, so that'll be -4 times -1. That'll be +4. No, let me do it this way first. I'm going to do it like this. I'm going to simplify it at the end. It'll be easier. Okay, so we have this at the top. Okay, then at the bottom we have -1 squared is 1, plus this one is 1 squared. That just means that we have square root of 2 on the bottom. Okay, but this formula says that after you find that magnitude, which is what this is, that you are to square it. So this will be the easiest way to just get one coefficient and then multiply it by the vector. Get it done like that. Okay, so we have -4 at the top. And this is just the vector W, which we're eventually going to multiply by that vector. The -4 came from us doing the dot product, -7 plus 3, which was this -4. Then we did the magnitude of W, but then we're supposed to square it. So we got square root of 2, but then when you square that, you just get 2. So this is going to end up being -4 divided by 2, -2 multiplied by -1, +1. So now just bringing that in, let's get a single number and then drag it into the vector at that point. That'll be the easiest for you. So -2 times -1, 2. -2 times 1, -2. So this is vector V1. And this vector is came from the formula that produces a vector that is parallel to vector W. Okay, we've also been asked to come up with a vector that is orthogonal to W. So when you want to come up with the vector that's orthogonal to W, then you use this formula. Okay, this the one that has so much information in it, so many calculations, is the one that's parallel. And then to get the other one that's orthogonal, it's just going to be the original vector V, which is 7, 3, minus vector V1. Okay, this is original vector V, and you're subtracting vector V1 according to this formula to find the orthogonal vector to W. So V1 was 2, -2. So it's front minus front, and back component minus back component, which gives you 5, and then 3 plus 2 is also 5. And so this turns out to be V2, which is orthogonal. Oops. Slide this up a little bit. Okay, so I'm just following the formula that's up above to find the orthogonal vector to W. I have to take the original vector V and subtract the parallel vector to W, which turned out to be 2, -2. So this is orthogonal to vector W. Okay, let me just check over this work real quick before we pass on to the next problem. 2, -2, and then 5, -5. Okay, parallel and perpendicular. Okay, last problem. We're doing a decomposition one more time. And in the decomposition, this time we have vector V with components 2 and 1, and vector W with components -8 and -1. And by the way, on that last problem, as is the case with all of these problems, you can put them in IJ form for your final answer if that's what's required. This would just be vector V1 would be 2I minus 2J. And vector, this would be the parallel one, just as it states over there. And the orthogonal vector to W would be 5A plus 5J. If you're asked to write it like that. Okay, because sometimes they give you multiple choice as the answer and you're expected to pick one of those. Okay, so decomposition once again. Okay, following those formulas that we just used, we're doing let's just review the formulas. In order to find the vector that is parallel to W, you're going to do a dot product times W over the magnitude of W. Okay, dot product of V and W times vector W over the magnitude of W squared. Okay, so let's go and grab those numbers. Oh. I left the door open. Okay, so this is V1, and this will be the parallel vector that we're going after right now. Parallel to the W vector. Okay, so dot product would be front component, coefficient of I, times coefficient of I here. Front component times front component plus back component times back component would be 1 times -1. Okay, then we're going to be multiplying that by the entire vector W, -8, -1. We'll leave that at the top. That magnitude for W is just the length of W, which is -8 squared plus -1 squared. I'll try to write that a little bit better. Okay, so trying to clean this up, this will be -16, and don't forget that after we find this magnitude, better put that right now that we are squaring that. So -16 plus -1, or just -1, same thing. -16 plus a -1 is -16 minus 1. We'll be multiplying that by the vector 8. Negative 1. Okay, down here at the bottom, we have 64 plus 1. So we have square root of 65 down here at the bottom. Cleaning that up just a little bit further, that would be negative 17 at the top. And once we take this magnitude, which is square root of 65, don't forget, once again, we are supposed to square that. So this would just be 65. So square root of 65, square root of 65. And then we have that vector W off to the side that we're supposed to be multiplying by. Okay, so there it is, much more cleaned up and simplified. And so V1, bring it down here. Is, let's distribute now. Now that we have, this can't be simplified any further, so let's just go ahead and drag it into this vector. So it's this times this, as well as this times this. So negative 17 times negative 17 over 65 times negative 8 for the front component, and negative 17 times over 65 times negative 1 for the back component, which gives you, let's get the calculator going here. So negative 17 times negative 8 is 136 over 65. That is your front component. And then the back component is just 17 over 65. Okay, if you want to write that in IJ form, it's 136 over 65 for your I component and 17 over 65 for your J component, if you want to write it in IJ form. Whatever is required in the question, they'll show you what they want. Okay, then if you're going, so this is V1, which is the vector that is parallel to vector W. Okay, then if you want to get V2, the formula for that, review this once again, is vector V minus V1, vector V minus V1, to find the vector that is orthogonal to W. So vector V minus V1, and that would be, let's see, what's vector V? We have 2I plus J, if you want to leave it in the IJ form, minus 136 136 over 65 on that I term, and 17 over 65 on the J term. You can actually leave the symbols like this. You don't have to use this when it's in the IJ form. That's for component form. You can leave them as parentheses right now. So now combining I with J, and you can get your calculator to do this. Okay, so you can just, for your I term, it'd just be 2 minus 136 over 65. 2 minus 136, let me put this up here so you can see it, divided by 65, and then just instead of hitting enter, hit math, enter, enter. Math, Enter, enter. That way it gets a common denominator and it reduces it for you. So on those I terms, it's negative 6 over 65. On that I term. And then likewise on the J term, it's 1 minus 17 over 65. So 1 minus 17 divided by 65. Hit math, enter, enter, so it gets a common denominator and reduces it. Okay, so that was positive 48 over 65 as the coefficient of your J term. And that's vector V2, which is perpendicular to vector W. Okay, so we found a vector that was parallel to W, and we found a vector that was orthogonal to vector W. Okay, I believe that is the last problem here. Yep, and that concludes section 9.5, dot products.